previous video, we talked about the multiplication of matrix with matrices, with another matrix. So we said that the multiplication is possible only when the number of columns in the first matrix is equal to the number of rows in the second matrix, okay, which is very, very important. So now we will be going into determinant of a square matrix. Okay, remember, for a square matrix, the number of rows is equal to the number of columns. Okay, the number of rows is equal to the number of columns. Okay, so in that case, let's take a 2 by 2 matrix. Okay, let's assume we have a 2 by 2 matrix of A, B, C, D, and we want to take a determinant. So when we want to evaluate determinants, okay, we have two straight lines. We have two straight lines to say that, oh, this is the determinant. Okay, so when we are given this, the determinant will be the leading diagonal. Okay, and the leading diagonal is this. Okay, the leading diagonal subtracted from the following diagonal. Okay, so in that case, it will be AD minus BC. Okay, so let's take, for instance, I have we have 1, 2, 3, 4. Okay, so the leading diagonal in this case is 1 and 4. Okay, that's 1 multiplied by 4 minus the following diagonal in this case is 3 and 2 minus 3 times 2. Okay, so that will give us 4 minus 6, and that will give us minus 2. Alright, so let's take another example for a 2 by 2 matrix. 1, 6, 4, 0. Okay, now we take the leading diagonal. Okay, and we take the product of the leading diagonal. We take the product of the following diagonal, and we make our subtraction. That gives us 1 times 0 minus 6 times 4. Give us 0 minus 24, and give us minus 24. Okay, and we can also have 6, 4, 4, 6, and 1, 0. Okay, we take the leading diagonal. Okay, that's 4 times 0. We take the following diagonal. That's 6 times 1. And our answer is 0. Because 4 times 0 is 4 times 0 is 0. And 6 times 1 is 6. That will give us minus 6. Okay. Now, since we have been able to evaluate leading diagonals subtracted from is leading diagonal subtracted from the following diagonal for as regarding a 2 by 2 matrix. Now let's go ahead and try and evaluate determinants of 3 by 3 matrix. Okay, for a 3 by 3 matrix, let's say we have A, B, okay, C, D, or instead we use our normal matrix notation. A11, A12, A13, A21, A22, A23, A31, A32, A33. Now this is a 3 by 3 matrix. Okay. Now since we know that we are considering leading diagonal minus following diagonal. However, the leading diagonal here is 3 components, like we have seen in diagonal matrix. Okay, Now, if you take the following diagonal, in this case, and we're able to evaluate maybe the product of everything. Now we are left with 1, 2, 3, and 4. Now the question is, they once they all have to come into consideration while performing the determinant operation. Of course they will. So there is now a much better way. It splits them into, take it bit by bit. Okay, so we will consider using splitting them into cofactors, or not cofactors, but into small values into 2 by 2 matrix. Okay, so the first rule we have to notice is that we are the order of sign. Okay, the appropriate sign values are given by plus, minus, plus, minus. Okay, minus, plus, plus, minus, plus, minus, plus, minus. Okay, this is the order. Okay, and the appropriate signs are given by the alternate plus and minus from top left hand corner, which carries a plus sign. Okay, so in that case we'll have plus, minus, plus, and you can also have plus, minus, plus. Now we'll be considering using A11, A12, and A13 as our determinant. Okay, as the determining value of how we will divide the cofactors. So let's go over and let's draw it again. A11, A12, A13, A21, A22, A23, A31, A32, and A33. Now let's consider taking A11 first. Okay, consider taking A11 first. I want to reduce, take a corresponding matrix formation, 2 by 2 matrix formation. Then in that case, this is A11. Okay, we take a look at the horizontal connection and also take a look at the vertical connection. Now the resulting part, okay, you can say that this is the resulting part. Okay, yes, this is the resulting part. So the resulting part is what will come to the 2 by as the 2 by 2 matrix. Okay, so we're having A22, A23, A32, A33. Now that will be for A11. Now let us now consider for A12. Okay, let's consider for A12. Now if we look at A12, if you look at A12, we will see that if we'll take a look at the horizontal, we tag the horizontal, and we also tag the vertical. What will we be left with? We'll be left with 1, 2, 3, 4. Right? So those are the 4 variables, the 4 elements that will enter into the 2 by 2 matrix. So with respect to that, we'll have this. This. So let's say we have A21, A23, A31, A33, and we have A12. And finally, we want to consider A13. Okay. Now, if we are going to consider A13, we will look at the horizontal and Look at what is connecting us also to the vertical, and what will be the remaining terms. Okay, the remaining terms will be this: 821, 822, 831, 832. Okay, so with respect to that, A13 and this 821, 822, 831, 832. Okay, now since we know the order that we have generated, that it is plus minus plus is a standard. Okay, so definitely A11 will be positive, A12 will be negative, A13 will also be positive. Now this is the way to solve the determinants. Okay, then we now go ahead and we say A11. Remember, this is leading diagonal minus the following diagonal. That will give us 822, 833 minus 832, 823 minus A12, 821, 833 minus 831, 823 plus A13, leading diagonal 821, 832 minus 831, 822. Now, the rest is to solve this is to take examples, okay, so that we are not speaking gibberish. So let's say we have 5, 2, 1, okay, is equal 6, 3, and 8, 4, 7. Okay, and we want to evaluate the determinant. And we know, of course, that we are considering the top values. Okay, in some books we can consider this. Okay, but however, we stick to this. Okay, so we are talking about 5. Okay, 5 will reduce. Remember, is plus minus plus. Okay, so it is positive 5 minus 2, which is on 2 by 2 matrix, and finally is plus 1, which is on 2 by 2 matrix. So if we consider 5, okay, we look at 5, and then what are the values on its horizontal, what are the values on its vertical, and the question is what are the elements left. Okay, we realize that these are the elements left, right? So for 5 we have 6, 3, 4, 7. All right, and then we go into 2. The 2 we look at the horizontal, we also look at the vertical. What are the elements left? We have this, and we also have this. Okay, so for 2 we have 0, 8, and we have 3, 7. 0, 8 and 3, 7. Now it will be very long. Instead of writing 0, 8, 3, 7, we write 7, 3, 7, 0, 8. Now, this will be wrong. Okay, we have to write in the order like this. Okay, so in that case, it will be 0, 8, 3, 7. And finally, if we consider 1, okay, 1 on the horizontal, 1 on the vertical. Okay, what are the values left? We are left with 0, 6, and 8, 4. Okay, so we have it's 0, 6, and 8. And then we can simplify further. Now we have 5. The leading diagonal here is 6 times 7, right? That's 42. Minus 4 times 3, that's 12. Minus 2 into leading diagonal of 0 times 7, that's 0. Minus following diagonal 8 times 3, that's 24. Plus 1 into leading diagonal of 0 times 4, that's 0. Minus following diagonal of 8 times 6, that's 48. And that will give us 5 into 30 minus 2 into minus 24 plus 1 into minus 48. That gave us 150 plus 48 minus 48, which gives us 150. Right? Now let's perform another example. Now let's pick example 2. We're given a 3 by 3 matrix. 3, 2, 5, 4, 7, 9, and 1, 8, 6. Now remember that we are dealing with 3 to 5. Okay, and it is plus minus plus. So determinant will be positive 3 having a square matrix, negative 2 having a square matrix, and plus 5 also having its square matrix. Now let's start review. We start with 3. We look at the horizontal value, we look at the vertical element also. And what are we left with? We're left with 7986, right? And then we write it 7986. And we move on to negative 2. Okay, and what are we going to be left with when we take so the elements on its horizontal and the element on the vertical? Right, we are left with 4196. Okay, so in that case we'll have 4196, 4916, and then finally we look at the plus 5 element. Okay, and the plus 5 element, we will look at horizontal, we look at the vertical, we will be left with these two. Okay, so that means it will be 47 and then 18, 47 and 18. So with this, it will be easy for us to evaluate the 2 by 2 matrix. We take the leading diagonal. Okay, now the leading diagonal in this case is 7 times 6. Okay, and 7 times 6 is 42, minus, and 9 times 8, that's 72, minus 2. We take the leading diagonal first. That's 6 times 4, that's 24, minus 1 times 9, that's 9, plus 5 into 4 times 8. That will give me 32, minus 1 times 7, and that will give me 7. So in that case, we have 3 into minus 30, minus 2 into 15, plus 5 into 25. After all these events of our final answer will be 5. Okay, and finally we'll take a final example of 3. Okay, let's take 3 of 2, determinant of 2, 0, 0, 0, 5, 0, and 0, 0, 4. If we do before, we know it is plus, minus, plus. Okay, and then we are considering the topmost value in first row. Okay, so that will be plus 2. Right, which will have a square matrix, minus 0, which will have a square matrix, plus 0, which will also have a square matrix. Now we can start with plus 2. Okay, so plus 2, when we consider the horizontal values connecting to it and the vertical values connecting to it, we realize that all we are left with is 5004. And when we look at 0, okay, minus 0, we will consider the two values, horizontal and vertical. Then we realize that we are left with 0004, 0004. Okay, and finally we are considering the final 0. We look at the horizontal, we look at the vertical, right, and we left it 0, 5, 0, 0. So in that case, we have 2. The leading diagonal here is what? 20. Okay, minus following diagonal is 0 times 0, minus 0 into 0 times 4 plus 0, minus 0 plus 0 into 0, 0 times 5 is also 0. Now you can see that everything here tends to 0 and everything here tends to 0. So we are left with 2, 20, and our answer is 40. Okay. Now, quickly, we will want to talk about transpose of a matrix. Transpose of a matrix. Now, what do we mean? What do we mean by when we say transpose? A matrix is being transposed. Okay. Now, transpose is where the row and column of a matrix are being interchanged. Okay, such that the first row becomes the first column, the second row becomes the second column, the third row becomes the third column. All right. So let's take, for instance, we have a matrix notation of A11, A12, and A21, A22. Right? Let's say it's called it A. Now the transpose of this matrix, which will be A transpose. Okay, the T stands for transpose, right? And or some, so we might write it as or A bar. But for easier understanding, we will stick to A transpose. Okay. We know that in transpose, the row, okay, and columns are interchanged. Right. Now, if the rows and columns are interchanged, definitely we know that this is a column that will become a row, and this is a row, another column that will become a row. So our first column, okay, it is a column here, but it will become a row here, and we have A11, A21. Okay, column 1 should become row 1, and then we'll have column 2, which will become row 2. That's A12, A22. Now it's as easy as that. So let's take an example. Let's say we have A to be 1, 2, 3, 4. Right? So our A transpose will be equal. We change the first column. Okay, let's call it C1, column 1, and we will change it to row 1 here. Okay, that's 1, 3. We take the second column, that's column 2, and change it to the row, because the rows and columns are being interchanged. Okay, that is 2, 4. Right? So now transpose of a matrix is not limited to square matrix. So we can have let's say we have a 3 by 2 matrix. Okay, a 3 by 2 matrix where we have 4, 6, 7, 9, and 2, 5. Okay, and then we want to perform our transpose of the matrix. Let's call this B. So B transpose will be equal. We take okay, let's start with it. The first column, right, and it becomes the first row. I'll give us 4, 7, 2. And we take the second column, and it becomes the second row. 6, 9, 5. Now, what do we observe? What do we observe? Now, if we can see here that the order of B, okay, is 3 rows, 2 columns, right? So that's the order is 3 by 2, and the order of B transpose is 2 rows, 3 columns. That's 2 by 3 matrix. Now we can see that the rows and columns are being interchanged. Okay, so if we have for a matrix in conclusion, so if we have a matrix of m by n, okay, and the transpose, the order, the transpose of the matrix, we realize that the m and the n had been interchanged, so it becomes n times n. Yes, so it becomes n times n. Now we can have as many complex matrices as we want. So let's take that C as equals to 276,315, and we are asked to look for C transpose. Now in C transpose, we take the first column, column 1, so become the first row, row 1, so that's 2 3, okay, and then we take the second column, column 2, that gives us the second row, 7 1, and we can also take the third column, column 3, that gives us the third row, that's 6 5. Okay, so transpose is as easy as that. And there is a very particular thing about transpose, and okay, so and that is the determinant of a square matrix, the determinant, okay, of a square matrix has the same value as that of the determinant of the transpose matrix. Now this is very important. This is very important, such that when we look at the square matrix, let's go back to the square matrix we had from the beginning. Okay, let's take this for example. Okay, let's take 1 2 3 4, and we know that the determinant is minus 2. Now if we take 1 2 3 4, we know that the determinant is minus 2. Now let's perform the transpose operation on it. Let's say this is A. Okay, now A transpose will be equal, okay, determinant of A transpose, let's rewrite this question well. We're given that A is 1 2 3 4, and when we evaluated determinant of A, which you can write as determinant of A, or we can write as A is equals to 1 2 3 4, which is equals to minus 2. Now if we evaluate the transpose of A, the first row, which becomes the first column 1 3, and the second column, which becomes the second row, that's 2 4, right? And we are asked to take the determinant of A transpose. Okay, that will give us A transpose, that will give us the determinant of 1 3 2 4. Now if that is the case, take the leading diagonal, that is 4, minus this following diagonal, that is 6. Okay, that's because 2 times 3 is 6, and 1 times 4 is 4, and the answer is minus 2. You can see it's the same as this. because the determinant of a square matrix has the same value as that of the determinant of the transposed matrix. Now, if that is the case, now let's pick a 3 by 3 matrix. Let's pick this 521063847, and the answer is 150. Even B, let's say B is 521063847 and 847, and we know that the determinant of B, which you can write as B, is equal to 150. Now I want to evaluate the determinant of the transpose of B. So we evaluate transpose of B, where the column, okay, becomes 0, 5, 0, 8. The second column becomes the second row, 2, 6, 4, and the third column becomes the third row as 1, 3, 7. Now we perform these as we have been doing in 3 by 3 matrix determinant. So we have 5. Okay, remember it is plus minus plus, right? So we have plus 5, which is square matrix, minus 0, which is square matrix, and plus 8 also, which is square matrix. Now if that's been the case, let's still use this for this video. We have 5, and we know that 5 is here, so we have 6, 4, 3, 7. If we take 0 again, we know that the remaining values is 2, 4, 1, 7. And if we take 8, we know that the remaining values will be 2, 6, 1, 3. After that being done, we have 5 in terms of 47 minus 42 minus 12 minus 0 into 14 minus 4 plus 8 into 6 minus 6. Okay, so we can now say that this is 5 into 30 minus 0 into 10 plus 8 into 0. Now obviously these two cancels out on 5 into 0, so we have 5 into 150. And we can see that the determinant, okay, the determinant of B transpose is the same as the determinant of B. Okay, now this works for a square matrix. Okay, now let's take a look at singular matrix, a special matrix which we call that singular matrix. Okay, now singular matrix is that whose determinant, okay, is 0. Okay, now in that case, if we're talking about the determinant of 0, let's take an example. 2, 0, 0, and we have 0, 1, 0, 0. Okay, okay, this is 2, 0, 0, and let's have 1 here. Let's also have 1 here. Okay, and also have 1 here. Also have 1 here. All right. So now, if we are given this matrix and want to evaluate the determinant of the matrix, we know that this will give us plus 2 into 1, 1, 1, 1, plus minus 0 into 0, 1, 0, 1, and plus 0 into 0, 1, 0, 1. And this will give us 2 into 1 minus 1 minus 0 into 0 minus 0. plus 0 into 0 minus 0. And this will give us 2 into 0 minus 0 plus 0 and altogether 0. Now this is a singular matrix because its determinant is 0. So with that, we'll stop here for now, and in our next video we'll be talking about cofactors of a matrix. Okay, cofactors of the square matrix. And afterwards we'll talk about the adjoint of a square matrix, and if time permits us we'll also talk about the inverse also of a square matrix. It because it's quite fun. Okay, because we are repeating um processes. Okay, because we've done the main work of matrices. Okay, so for that we see you there.